Welcome. In this video, I will state and prove a theorem on the distance between a point and the tangent line to a circle, where the circle represents uniform circular motion. And for context, you can imagine that you're swinging some object, and then at some point you release it. And what will happen is this object will follow the tangent line. Okay? And maybe you want to hit something, or you want to avoid hitting something with some kind of safety margin, right? So let's draw our circular motion here. So we have, try to draw a circle here, and then at some point, boom, we release this, all right? And that means that we will follow the tangent line at that point. It'll go in both directions, but I'm more interested in the direction of motion, right? Okay. And then, down here somewhere, we have our target point that we either want to hit or we don't want to hit. Beautiful. Okay, so let's get a representation of this uniform circular motion here, okay? So this object here will have a center, and then I'll go one radius in some kind of direction here, okay? And the direction will be represented by this unit vector. Right, so we have the center here, which is represented by the C, and then we go R unit vectors this way, where this unit vector here is really this thing that just gets scaled out to the periphery of the circle. All right, okay. Now how do we represent this tangent line? Well, we represent this line in a similar way that we do with a lot of other lines. Is we use the equation for the line. Okay? And in this case, the A and the B are just going to be represent the x and y coordinate for some normal vector. And in this case, we have this beautiful little normal vector here that is this unit vector. And that it being a unit vector is going to make our lives way easier later on. Okay? So the cosine and the sine are going to represent the A and the B in this. All right? So the only thing that's really left is this C value. So what's going to be the value of C? Well, as it turns out, the C, or the minus C, is always going to be this evaluated at some point on the circle. Well, we already have a point on the circle. We have this point. We have the point of release. Okay, so C, minus C is always going to be this point here. So it's going to be the C1, the x-coordinate for the center of the circle, and then plus r times cosine of omega t, right? So it's going to be the x value, and this we need to multiply by the a value from up here. So that's going to be another cosine. Right? For the and we do the same thing for the y value. So we're going to get the C2, and then we're going to plus r times sine of omega t, and then times sine of omega t. All right? Okay, we can expand this, and what we're going to get is we're going to get C1 times cosine of omega t. We're going to get C2 of sine of omega t from over here. And then we're going to get these r terms. Okay, so there's going to be a plus r, and then we're going to get cosine squared of omega t plus sine squared of omega t. All right, and hopefully you know, or you can find out pretty easily, that the cosine squared plus the sine squared is actually always just 1. So this is just basically Pythagoras in the unit circle. Okay, so this is our C value. It's not too bad. Just this, and then we just kind of moved it by this one radius, which makes kind of sense in this context, right? So that's our C value, okay? So now the theorem is that the distance, let's put it up here, the distance between this tangent line T and this point down here that we call P is going to be the absolute value of P1 times cosine of omega t plus P2 of cosine of omega t plus C. Shoot. And we'll see if this is correct. So the white formula is R theorem. Cool. Well, let's apply this. Okay. So the way we do this is there are two ways. The first one is to create some imaginary point here, just called x1, or sorry, x0, y0. All right. And then creating a vector from there to here. All right. And then we can take this the scalar product with this normal vector, and since they're parallel, the angle will be either 0 or 180 degrees. But that will mean that we will technically not get an angle component in the following formula. Okay? So we can take this, the scalar product between these two vectors, and we call this vector, vector A. So the scalar product between and the normal vector to the line is going to be the length of A times the length of the normal vector, and then the cosine of the angle between these two. Okay? But because they're parallel, this cosine will just be a plus or minus 1, right? And the length of the normal vector here is chosen to be 1. So this is exactly the object that we're interested in. We're interested in the length of this. And then we just have to ignore the sign here if you want to find out this magnitude. All right? So let's try to do this. Okay, let's take the scalar product here. Okay? So it's going to be these two objects subtracted. So that's going to be, so this is going to be P 1 minus x0, and then we have to multiply by cosine, and then we do the same thing with the y coordinates. Beautiful. We can expand this, and what we'll get is P1 cos of omega t plus P2 of sine omega t, and then minus x0 cosine of omega t minus y0 cosine of omega t. The beauty of these x0 and y0 is that we actually don't care what this point is, because for every single point, the c value will always just be any point on the line where you multiply the x coordinate with the x component of the normal vector, and you multiply the y coordinate with the y component of the normal vector. So this thing here will always be c, regardless of what you choose. And that's what the formula says. I wrote cosine twice. Ignore that. Beautiful. Okay? There's one more proof of this, if you prefer, and that is to consider the projection here instead. So you take the projection from this point C to P, and then you take this length here. So you take the projection down here, that starts here, and then you just add or subtract. So this is going to be minus the normal vector times r. Okay? All right. So this length, the length that we're interested in, is going to be the length of this vector. So it's going to be the length of the vector that goes from the center of the circle to the point P, and then we project this onto the normal vector. Right? And then we have to subtract n times r. Okay. Well, what does the formula for the projection say? Well, it says that it's going to be this vector scalar product with the normal vector, and then we divide by the length, the magnitude of this vector squared, and then we have to multiply it by the vector we're projecting on. Okay, still the length. The c comes up here, and then we subtract n times r. It's beautiful. Well, what is the this length here is just 1 because we've chosen it again to be a unit vector, and then we have this. So we're really interested in this scalar product. We have a common factor here of an n, which is I'm going to take outside the parenthesis. Okay, so we're going to get c. Okay, so this is going to be p minus p1 minus c1 times cosine of omega t, and then plus P2 minus C2 of sine of omega t, and then we subtract the r, and this whole thing gets multiplied by n, right? Since we have a common factor of n here, all right? But when we take the length of this is something multiplied by a normal unit vector, okay? So we can actually just cancel this. So the length of this is just going to be the absolute value of whatever this is, okay? And again, if we expand this, you will actually see that what we get is, I'll write it up here. What we get is, we get P1 cosine of omega t plus P2 of multiplied by sine of omega t, and then we get this thing, minus C1 cos omega minus C2 sine omega minus r. That's exactly what I showed earlier. It's the same as c. So again, we get a plus c. All right? So the second proof of this theorem. Personally, I think this is more elegant because it draws in this, this representation of the tangent line. All right? If you have any questions or comments, leave them below.